Today we are continuing with the concept of the Lewis bond theory, and the next step is to talk about the Lewis structures. So to do a little recap here, when we refer to the Lewis bond theory, we are trying to explain how atoms form bonds, okay? And what this theory uses is valence electrons. And for us, for all practical purposes here, the valence electrons are those in the last shell. And for any atom in the periodic table, the last shell usually are the s and p orbitals. And remember, we have 2 electrons in the s orbital, we have a maximum of 6 electrons in the p orbital. So for any given atom, the maximum occupancy in the last shell is 8 electrons, and we refer to do, if they complete 8 electrons, we call that noble gas configuration. Pretty much. Okay? So initially we've been talking about Lewis bond theory to explain the ionic bond, and for example, if we have, let's say, sodium and chlorine, let's keep it very simple in this case. We have one valence electron for the sodium, and here for chlorine we have 6 valence electrons, and therefore when they form a bond, this electron from sodium is completely transferred to chlorine. So these are the neutral atoms, that's the Lewis symbol look for the neutral atoms, and when they form the bond, then you have sodium plus, because you lost that electron, and then we have chlorine 1 minus, and that chlorine has 8 electrons around the last shell. So pretty much that's how the ionic bond forms. Now with Lewis structures, we are aiming to explain the covalent bond. Okay, because there is not much to see here in the ionic bond. It's just two oppositely charged particles that attract themselves, and that's what forms the structure of the compound. But with the covalent bond, the story is a little bit different. So again, remember, we have 1 dot for the Lewis symbol, we have 1 dot for each valence electron. And the Lewis structures, we are just focusing on those electrons. We forget about everything else. We forget about even the d orbital sometimes. The d orbital electrons, we forget about those sometimes. Okay, main group, we are only interested in the s and p orbitals. And that refers to the largest value of n, the principal quantum number. Okay, these are 4 orbitals, means 8 electrons. So if we have here the nitrogen atom, the last shell is that. So we actually forget about this. All we care are about those 5 electrons. And when you draw the symbol, the Lewis symbol for nitrogen, it's going to look something like that. Now, if you remember, if we picture if we use the graphical representation of this configuration of the last shell, we're going to have something like this. This is the 2s orbital, and this is the 2p orbital, and we have 2 electrons here, and we have all those 3 electrons are in a different p orbital. So when you draw your Lewis symbol, that Lewis symbol is going to look pretty much like the graphical representation of those 4 orbitals. Okay, even if you have 5 electrons here, you will not put 2 electrons together here, because that's somehow is violating Hund's rule, if you remember that. So that Lewis symbol somehow will resemble the graphical representation of those orbitals. So keep that in mind. Now, in the covalent bond, remember, ionic is transfer of electrons, the covalent bond is sharing of electrons. So basically here we have, in this case it's just 2 fluorine atoms, we have that unpaired electron here, and technically if they were forming an ionic bond, then that electron would go to one of the fluorine atoms, but it's the same atom, they are fighting equally for that electron. So it ends up being they sign a treaty, so to speak, and those 2 electrons are in between the atoms. So those 2 atoms are held together because they are sharing those electrons right in the middle. So usually it's a little more confusing if we keep those two electrons showing like electrons, so we represent that bond with a line. So this bond here, a single line represents a bond. Okay, so if it's just one, it's 2 electrons. If it's 2 lines, a double bond, then it's 4 electrons. So, and they form that type of bond. They are sharing those 2 electrons because they are actually completing 8 electrons in the last shell. So if we forget about, for a moment, if we forget about these electrons being in the middle, and then you are trying to count how many electrons each one of those atoms are completing, then basically what you have here is that you count for fluorine, and this fluorine has 1, 2, 3, 4, 5, 6, 7, 8, and then the other fluorine has 1, 2, 3, 4, 5, 6, 7, 8 electrons in the last shell. So you count those 2 electrons, you are sort of counting them twice. Okay, so there is an exception to that, and that is the hydrogen atom, because actually for hydrogen we are saying that every element in the periodic table wants to be like a noble gas, but in the case of hydrogen in particular, well, the noble gas for hydrogen is helium, and therefore hydrogen wants to go for helium, and helium doesn't have 8 electrons in the last shell, it's only 2. So same thing here. For the water molecule, we have those hydrogens attached to the oxygen. You count the electrons for around the last shell for oxygen, then you will see 8 electrons here because you count each of those electrons from the hydrogen atom for oxygen, and then you count them for hydrogen. In the case of hydrogen, it's not aiming for 8, it's aiming just for 2 electrons. And that makes hydrogen more than happy. So it's a duet for hydrogen, it's an octet for everything else, except helium. So why do we use Lewis structures then? Well, it's simple. It's just drawing atoms with valence electrons and lines connecting the atoms. It allows us to explain how the bonding happens, and it does a good job doing that. And more than that, well, how we understand how the electrons are being shared between the atoms. Okay, you can extend that even to the ionic bond, but there is not exactly a Lewis structure for ionic bonds like there is for covalent bonds. And here, one of the most important things that it provides us is that we can differentiate between single, double, and triple bond. And what does that mean? Well, we have 3 different types of bonds here, and again, these are covalent bonds, not ionic bond. The ionic bond is practically just one type of bond, but the covalent bond can be single, double, and triple. The main difference is that in a single bond you are sharing just 2 electrons. You put those 2 electrons in the middle, and you use a line representing those 2 electrons to connect the atoms that are sharing those electrons. Okay, so the lines will connect atoms sharing electrons, not with anything else. The double bond is 2 pairs of electrons, which means 4 electrons. So I will ask you to be careful here. Sometimes you will read something like pair of electrons, so 1 pair is 2 electrons, and sometimes you want to read something like total number of electrons, so you have to be careful with that. So in this case, the double bond is going to be 4 electrons, 2 pairs of electrons, and it's a double line, and you see where this is going. Triple bond, 3 pairs, you put 6 electrons in between those elements. Using the dots is a little more let's say annoying than just writing the line, so it's much easier to represent the bonds with lines. And remember, these are covalent bonds. So the octet rule that we've been mentioning, everyone wants to be like a double gas, so that's why we refer this to the octet rule. So because everyone wants to complete 8 valence electrons, and remember, valence electrons, electrons in the last shell. So for atoms sharing electrons, and that goes mostly for the nonmetals, the covalent bond is what allows them to complete those electrons. So in this case, this is the carbon tetrafluoride molecule. The carbon has 4 valence electrons. Each one of the fluorine atoms has 7 electrons, valence electrons. If you count the number of electrons for each one of those fluorine atoms, remember, you count the electron coming from the carbon for each one of the fluorine atoms, so they complete 8 electrons in the last shell. And when you count it for carbon, it started with 4, but each one of the fluorine atoms is providing 1 additional electron, so carbon gets to complete 8 electrons as well. Much easier to represent, those lines representing the bonds. And remember, those that you see here in pairs, these are the lone pairs. Lone pairs or non-bonding pairs. Of course, the bonds, these are bonds or bonding pairs. Okay, so what are the rules? Because we want to draw structures now, right? From a certain point of view, these are kind of structural formulas. So what do? Well, first step is we have to count the total number of valence electrons. Total number of valence electrons from all atoms in molecule. Not just one, from every single atom. If you have 3 of the same type, well, it's 3 times the number of electrons for that particular atom. If you have an anion or cation, well, you have to add or remove electrons accordingly. If it's an anion, you are supposed to add. If you have cations, you are to remove electrons. Okay, remember, because anions gain electrons, cations lose electrons. We write the skeletal formula, and it sounds kind of bad, but basically what you do there is you take the least electronegative atom and you put it in the center of the molecule. And we are going to keep this as simple as possible, so usually you will be handling just one central atom, which means pretty much you put everything around it. A couple of restrictions here: hydrogen and fluorine, they are always at terminal positions. Always. No matter what you do, hydrogen and fluorine will always be in terminal positions, which means they will never be a central atom. Now we connect all of those terminal atoms to the central atom. You start with single bonds. Okay, you connect everything with single bonds. And then remember, each single bond, as many as you have, each single bond represents 2 electrons. That will give you the number of electrons that you have used so far. And whatever you have left, then you start putting around the central, around the terminal atoms. Okay, we're gonna get to this in a moment. So those lone pairs in terminal atoms, you are aiming for completing 8 electrons around the last shell for each one of those terminal atoms. Remember, the section is hydrogen, which only 2. If you have lone pairs, if you have electrons remaining after you do that, then you put it in the central atom. Okay, so after you do that, then you check the number of electrons around each atom. You compare, at this point you are supposed to run out of electrons, so you don't have anything else. You have used every single valence electron that you started with. And if you have a situation in which there are elements that are not completing an octet, then you take lone pairs from terminal atoms and you move them to the central atom to complete if necessary. So we'll work on some examples later on. So counting valence electrons, this is really important. It's not just from one atom, you are counting the valence electrons coming from every single atom in the molecule. Okay, we add electrons for an ion, we remove electrons for cations. So how do we do this? Let's assume we have here the nitrogen trifluoride molecule. So we count for nitrogen. Nitrogen has 5 valence electrons. And then you have fluorine. You have 7 electrons, 7 valence electrons for fluorine, but you have 3. So this is 21. Therefore, you have a total of 26 valence electrons in that molecule. Okay. if you have the ammonium ion, so we still have nitrogen here, correct? So we still have 5 valence electrons. We have hydrogen. Hydrogen only have 1 valence electron, but you have 4 hydrogen atoms. So that is 5 plus 4 electrons. You have a positive charge here, meaning you subtract 1 electron, so therefore the ammonium ion has 8 valence electrons. Okay? Now the phosphate ion. We have phosphorus, and phosphorus has 5 valence electrons. We have oxygen. Oxygen has 6 valence electrons, but you have 4. That's 24. So if you add those together, that is 29 valence electrons. But you have 3, so it's plus 3 electrons here, so it's 29 plus 3, 32 valence electrons. The phosphate ion has 32 valence electrons. The ammonium ion has 8 valence electrons, and the nitrogen trifluoride molecule has 26 valence electrons. Okay, so remember, you subtract if it's an anion. You subtract if it's a cation. You add if you have an anion. Okay, so how does the water molecule works? So we have a water molecule, right? So it's oxygen, that's 6 electrons. Then we have hydrogen, is 1 electron times 2, that's 2. So this gives you 8 valence electrons. Okay, so you start with oxygen in the middle, then you put hydrogens on each side. It doesn't really matter at this point. So we connect with single bonds. So you have 2 single bonds here. That means 4 electrons, correct? You started with 8 electrons, so 4 more to go. You need to put 4 more electrons in that molecule. You have used 4. So you start with the terminal atoms, but it's hydrogen, right? If you can hear, hydrogen already have 2 electrons because it has 1 bond. Same thing for this hydrogen. So those 4 extra electrons go into the central atom. 1, 2, 3, 4. Now you count for oxygen. That's 2 bonds and 2 lone pairs. And 2 lone pairs. So that's 8 electrons. Oxygen is completing 8 electrons, and that is the Lewis structure for water. How about CO2? So we have carbon, which is 4 electrons. We have oxygen, which is 6 electrons times 2. That's 12, so we have a total of 16 electrons here. Correct? So carbon is less electronegative than oxygen. So we put everything around and we connect with double bonds. With single bonds. So we have, you started with 16. You have 2 single bonds at this point. So you have used 4 electrons, so you have 12 electrons to go. Okay? So you start in the terminal atoms, so that's oxygen, so that's 1, 2, 3, 4, 5, 6, and 2 more, that's 8. 7, 8, 9, 10, 11, 12. With 2 here, each oxygen is completing 8 electrons. So oxygens have 8 electrons. But when you look at carbon here, only 2 bonds, that's 4 electrons. Carbon only 4 electrons, so carbon is not happy actually. So let's draw the molecule again here. So it's carbon, single bond, oxygen. So now the rules here, or the guidelines, let's put it that way, is that if you have used every single electron, because you have done so, then you are supposed to move atoms lone pairs from the terminal atoms into the central in order to complete. So let's say that we take this lone pair and move it here. So that's carbon, double bond. You use those lone pairs, so you only have 2 more lone pairs here. And at this point you are looking at this. If you just leave it like that, carbon is completing 6 electrons in the last shell only. So you have the option of using another lone pair from the same oxygen, or you take another lone pair from, just kind of keep it symmetrical. Sometimes you are also aiming for that. So now you have carbon with 2 double bonds, that's 4 electrons. And if you count each oxygen, 2 bonds, that's 4 electrons, plus 2 lone pairs, 4 more electrons. So you have 8 electrons here, you have 8 electrons for carbon, and you have 8 electrons for the other oxygen. So this is how you do this. There are few exceptions to this octet rule. Remember, you are trying to complete 8 electrons, except for these cases. There are 3 main cases. There are odd electron molecules that they excuse me, they cannot complete 8 electrons even if they wanted to, because it's an odd number of electrons. And usually you will see that everything that you're going to work, except in these cases, is an even number of electrons. And when you have that case, it's easy to complete the 8 electrons. If you have an odd number, not so much. So the other case is electron deficient molecules. These molecules tend to not complete 8 electrons. So usually they are a little short. Usually they complete either 4 or 6 electrons in the last shell, and they are more than happy to do so. Energetically, it's more favorable to just do that than trying to get the 8 electrons. And probably the most common is the hypervalent molecules, because in this case those atoms are able to hold more than 8 electrons in the last shell, but more on that later. So in the case of odd electron molecules, that odd number of valence electrons is what's getting in the way. So here nitrogen, this is a lone electron, not a lone pair. So that electron, even if you take 1 electron from the oxygen, the oxygen then is going to be incomplete. So this is what we call free radicals, and they are, you remember, every single element wants to be like the noble gas, and here this nitrogen has 7 electrons. And what did we say about the halogens? The halogens are very reactive because they are just 1 electron away from the noble gas configuration. So these free radicals are also very, very reactive. Okay. Now this is more frequent. These electron deficient molecules usually have less than 8 electrons around the last shell. And for this case, I'm just gonna, kind of point you in the right direction by saying if you see boron, if you see beryllium, sometimes even aluminum, it will give you those cases. Okay, here beryllium, only 4 electrons in the last shell. Beryllium is a rather small atom, and it's more difficult for it to hold more electrons in the last shell. So beryllium actually will have to take 4 more electrons to complete the octet. So beryllium said, "Now, you know what? I'm good. 4 electrons is more than enough for me." Boron does the same thing, except that boron has 3 electrons in the last shell, can form 3 bonds that complete 6 electrons, but same as beryllium, boron, these two are just happy. They are happy with incomplete. They don't mind. Okay, so again, boron and beryllium are your cases. Aluminum, possible. So those are the frequent cases in which you see electron deficient molecules. More frequent are the hypervalent molecules. Here, those atoms, those central atoms, it's always about the central atom, can get more than 8 valence electrons, and they can do so because they have some other orbitals that are available. So let's begin by saying that second period elements cannot do it. Okay, second period elements. Who are second period elements? carbon, nitrogen, oxygen, fluorine. None of them can form expanded octets. But the third period elements, there is an empty d orbital that they can use. Okay, they use those d orbitals to hold those valence electrons, or at least exist the possibility that those extra valence electrons can go into the d orbital. So what are the third period elements? Those that are below this order. So you have from carbon, that's silicon, phosphorus, sulfur, chlorine, and anything underneath those four will also be able to form expanded octets. So how do you know if you have an expanded octet? As we say, that's more frequently. So if you follow all the rules in drawing that Lewis structure, and if everything is connected, and if you have used all the electrons and everyone has the satisfied octet and you still have valence electrons, then that's an expanded octet. Okay, remember, if you follow the rules, everything is connected with single bonds, everyone has completed the octet, and you still have electrons to go, then that's an expanded octet. And if you have extra electrons, always go to the central atom. So let's take a look here. So we have sulfur tetrafluoride. Okay, sulfur is 6 electrons, fluorine is 7 electrons, but you have 4, correct? So that's 28. These added together, that's 34 valence electrons. So fluorine, most electronegative atom in the periodic table, go to terminal position. Actually, that's one of the reasons why the fluorine is always in terminal position. So sulfur is in the middle, and we connect all the fluorine atoms with single bonds to the central atom. Okay, so at this point you have 4 bonds. That's 8 electrons. We started with 34, so at this point we have 26 electrons to go. Okay, so we start putting electrons around the fluorines. 1, 2, 3, 4, 5, 6, plus 2 in the bond, that's 8. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, 4 fluorines, you put 6 electrons around each fluorine, that's 6 times 4. Let's say 4 times 6 electrons, that's 24 electrons. So that's 2 electrons to go. So each fluorine is completing 8 electrons in the last shell. The sulfur atom has 4 bonds around, that's 8 electrons. So everyone has 8 electrons around the last shell. You still have 2 more electrons to go, and guess what? It goes to the central atom. So these 2 electrons will go to the sulfur, and you just put it there. So sulfur has 10 electrons in the last shell when forming this structure. Now, PCl5. Phosphorus is 5 electrons. Chlorine is 7 electrons, but you have 5. That's 35. This is a total of 40 electrons. So we have phosphorus, and then we connect all the chlorine atoms. So you have 5 bonds. That's 10 electrons, right? And at this point, if you are seeing that phosphorus as a central atom, it already has 10 electrons in the last shell. So, but we started with 40, so 30 electrons to go. So 1, 2, 3, 4, 5, 6. Same for this one. Same for this one. Same for this one. And same for this one. You have 6 electrons around each chlorine, electrons in lone pairs. So that's 5 chlorines times 6 electrons. That's 30. We're even. We have used all the electrons. However, even if you don't have to put any additional electrons in the central atom already has 10 electrons around the last shell. So this is what we're going to be doing in class next time, and that's it for now.